will be demonstrating the effect selection has on a small population of lizards. The lizards in this area can be described as nearly identical, except for one genotype and its associated phenotype. They have varying tail lengths of short, medium, and long. Because our lizards are living a relatively good life without any pressure or natural selection, allele and genotype frequencies have arrived at Hardy-Weinberg equilibrium. To demonstrate this, the phenotype, which is a singular autosomal gene made of 2 alleles, of 100 lizards was measured. After measuring all of the lizards' tail lengths, the genotype frequency was able to be determined. Since we already knew how the genotypes related to the phenotypes, we were able to use the genotype frequency to calculate the allele frequency by adding half of the genotype frequency of the heterozygous individual to each of the homozygous individuals. This approach works because for each genotype we have 2 alleles, so for the 36 long-tailed lizards we have 72 big A's, and for the 48 medium-tailed lizards we have 48 big A's and 48 little a's. You can also use the Hardy-Weinberg law equation to double-check your answers. Our happy little lizards have been introduced to a devastating natural selection process as a gang of stray cats have been introduced to their environment. Although our lizards are fast, they are not fast enough, and after some time it is noticed that lizards with short tails have a higher chance of surviving our tiny feline terrors than the lizards with long tails or medium tails. This is an example of a directional selection. The cats have a rather harsh relative fitness effect on our long-tailed lizards, as our cats slowly exterminate most of the long-tailed lizards before they ever have a chance to reproduce. Extermination will have a dramatic effect on the future phenotypical ratios of lizards. And we can use the genotype frequency and our relative fitness to calculate the eventual phenotypic ratio we can expect of our lizards. To determine the genotypical frequency of our survivors, we simply multiply the genotype frequencies that our lizards presented before selection with their relative fitness rates. However, due to the effects of relative fitness has on our survivorship number, our total does not come out to 100% as it must in order to get an accurate measurement of the genotypical frequencies. In order to correct this, we simply divide our unadjusted survivor calculations by their combined total to get the correct genotypical frequency. As you can see here, our long-tailed lizards who started at 36% have decreased to 10.6%, our medium tails have decreased to 42.4%, and our short tail have actually increased to 47%. This is due to the cats being able to capture and possibly eat the long and medium-tailed lizards quite frequently, preventing them from reaching reproductive age and passing their genes, making our short-tailed lizard most likely to reproduce and pass on its little a alleles. A fact that can be further demonstrated by taking our new genotypical frequency and calculating the allele frequency just as we did before selection. In this case, the stray cats are a selective pressure that will cause the allele frequency to more than completely switch, causing a directional shift towards the small allele. If this selection was to continue to occur, the eventual phenotypical ratio of these lizards would be 100% short-tailed. Thanks for watching!